Welcome everyone. Very good morning. I'll be talking today about applying machine learning and some war stories from application. I am a founder of AutoInfer, and I also lead a group at Soliton Technologies doing computer vision. So I'll jump right in. All right. So what do we do at Soliton very quickly? So we work on computer vision quite a bit, some amount of machine learning. We also have developed cameras, and this we've been doing for past almost 18 years. These are what called smart cameras. These are cameras with onboard processing, and so they can do sensing and all of the processing on board. Our latest set of cameras, they have optimized OpenCV and TensorFlow, etc., in order to do many of the machine learning and deep learning, deep learning. And it's all designed and manufactured in India, in Bangalore for the last 20 years. So some of the applications we worked on is one of them is analog gauge reader, where the algorithm automatically reads a analog gauge using computer vision. Another one is a very high accuracy handwriting character recognition, which essentially reads handwriting characters. So it's very similar to MNIST, but the difference here being that you have to do it, end to end, right? You have to detect where the character is, you have to segment out the character and then recognize it, and also have 99.9+% accuracy. So very high accurate system. Other things are, for example, markerless augmented reality. That is like augmenting on top of visual field objects, 3D objects potentially, or measuring 3D objects as well. So how do you precisely measure objects is another thing that we have worked on. I'll keep moving. So the first anti-pattern is, so everyone is talking about AI or machine learning or deep learning, right? And this is one of the one of the favorite anti-pattern, that is, they'll say, oh, let's use AI, and they'll say, oh, I'll apply it to solve problem, X, and most of the time it would be something one of these three, which is either it would be a very trivial use case where it will be like, I'll use deep learning to do spell correction, right? When actually you can use something much simpler, or I'll use deep learning to fit a line. All of which you don't need such a sophisticated machinery. Another case is where it's very complex in the sense that you need to have very encoded information that you need to be able to work with. So for example, and they would say something like, oh, Google Duplex does conversations, let me also do conversation, right? But the limitation here is that it's much narrow what Google Duplex does, for example, right? Which is, you can call, you can make an order, but for a very limited narrow skill sets is where it works for. It is not for, you cannot have, discussion with Google Duplex on, what is reality, for example, right? So that is the next one. And the last one is what I'll call complicated, which is where you have multiple modalities of input, right? Visual or other, speech and other things, right? And the example of that would be something like, they'll say, I'll replace doctors, with using machine learning or deep learning, whatever it is. So the takeaway here is that, AI is not a magic sparkle. It's not something you can just put and, suddenly all your problem goes away, poof, right? It is much more than that, and the nuances really matter. So if you are a decision maker, it's very important to understand these nuances. Only then can you really make those right decisions. It's not one cannot use it like a magic sparkle. And usually, I would hear things like, oh, why didn't we, use X technology to solve it, right? Like transfer learning or unsupervised or reinforcement or whatever it may be. So another one or two more takeaways here is that so get your hands dirty, go for attend meetups, etc., to get some hang of what is happening, and maybe people who already learned can teach you very quickly. And another thing I can say is that this Robert Noyce's quote, which is in research in general, people who are working at it are the best to give guidance, right? So talk to people who are working on it, either in your team, or trust them if they are the ones who are working on it. And hopefully this talk will help you. And one more thing here I would say is that also understand this curve. So there's an exponential curve. That is the amount of accuracy you need, right? That is the amount of effort you require sort of exponential. So the numbers are not necessarily, indicative. It's just more for approximation. And so the idea here is that, if you get 95%, you need to put X months. You have to put way more than, twice of X to get next level, right? So it's a very exponential curve. Right, so you need to understand where your problem is and how much effort you're going to put in. The last thing I'll say important is that understand the deep learning or machine learning for software lifecycle. What do I mean by that? So the initial phase of any machine learning project would be, you have a business problem definition, right? So you'll say I want to solve, say, face recognition under very restricted conditions. And then you will say, what, I'll give a bunch of images, I'll train the algorithm, I'll test it on the real field, and then I'll keep iterating, right? Till I can actually narrow the business problem very, very precisely. And why do I say to do it this way? Now, another way could have been I prototype it and immediately I take it to production, right? That actually would be it probably is a bad idea. The reason is that the moment you prototype a production, that requires a lot of engineering effort, right? And maybe this definition of the problem itself is different, or the technology you're using is, it might change, etc. Right? Meaning it might be solving well enough for you, right? So don't make your prototype production very quickly. At the same time, you can still take it out to the field. Okay? So the next anti-pattern is what I'll call crap in, crap out. You can just have a look at that. All right. So the idea here is that people are just throwing that, hoping you can just throw data at it and it'll just solve it for you, right? Thanks to XKCD. So in general, this is a setting, in under which I'm talking about. So most of it's under supervised machine learning setting, but it applies to other cases also. So the supervised machine learning setting is as follows: you have a bunch of images and their labels. So here, image of cat, and that is a cat. The information that is a cat, and you train the network to understand, or the model to understand that it is a cat and this is a dog, right? So you give a bunch of images, you train the network, and the network has information. This is the image of a cat, right? And it will learn that. Now, this is what's called the training procedure, and the test is where you give a new image of a cat and you want to know, oh, what is this, right? I mean, you don't know it's a cat. It's this image. Once one image, you need to figure out that it's a cat. The symptoms of crap in, crap out is that when you add any new data, the system suddenly goes haywire. Okay, that is one symptom of this crap in, crap out. Another would be where your model is on the knife edge. That is, you make a small tweak to your model and suddenly it's giving completely different results from what you had earlier. Okay, and the third one I would say is long repeated iteration loops. Meaning, so you developed a model to do one problem, and now the same problem you give more data, and suddenly you need to spend the same amount of time you took originally, if not more. Okay, in order to come back to the same one. So these all are symptoms of crap in, crap out, where you just someone threw a data at it, and if the model gave some output, it need not be the right thing, right? And so how do you ensure this doesn't happen, right? So first thing you need to make sure is that you need to look at your data, right? Use the tools to understand actually what is happening. Make sure there's nothing, data is kosher. There's nothing off in the input or the output. Look at samples of inputs, samples of outputs. Do a simple walkthrough of each stage, right? So for example, in this case, segmentation, I'm going through each stage and showing what is happening. So step through and make sure it actually is doing the thing it's supposed to be doing, right? Now, so this is the very basic set of tests. Once you do that, then you make sure, okay, can you fit this model? Can you get fit for a model, and can you at least overfit for the training data? Right? That is, your algorithm should be able to predict with very high accuracy, at least for the training data. When I say very high, I say 99+%. Right? If you cannot even overfit, you cannot generalize the model. Right? So first of all, try to make sure your model is capable of learning what you're trying to teach. Right? And then the next problem would be also one more thing to ensure is that make sure your test set and training set both have the same number. I mean, have same number of classes for each. So for example, if I'm training on cats and dogs, if I have 10 images of cats and 1 million dogs, network probably cannot learn about cats, right? And and at test time also similar issue will happen. Now at this point you probably have already got enough data. Now the problem is that you got large amount of data. How do you debug with large amount of data, right? So in that case, you have to build tools to do that effectively. So for example, in our case, we were doing this handwritten characters, and so we built this kind of a tool where I can see large number of ones very, very quickly, right? And in this particular case, what happened was that we figured out these kind of ones. It's very small here, but what we call continental ones, with the top part being there. That was not in our data set, right? And so then we had to augment those data and make sure the data was there in the system. So you build tools. I mean, whatever the tools may be. Maybe it's a simple tool like this, or like the next one where it's a more sophisticated tool. So here we are doing what's called the t-SNE embedding, t-stochastic neighborhood embedding, which is actually embedding of the original data into 2 dimensions, right? So this is, for example, the cluster of 2s. This is the cluster of 5s. And this tool actually is a JavaScript based tool which you can zoom into that area, and then you can actually see a small region. and see what those characters are, right? I mean, what those in the characters in this particular case. And now we can see, oh, why this is the case, why this is having a problem. So this could give you an intuition about, okay, why your model might be having difficulty, right? So build tools where necessary. And in this particular case, we build a web app in order to do that. Another one I'd say is that is also that I understand what is I mean that is and do a decent debugging of your system, right? That is, make sure that when you are having a problem, when the network is not predicting correctly, why is it not doing that? So one quick thing you can do, for example, is to debug your system, right? Using, for example, class activation maps. So these tell you, for example, what regions of the image was responsible for making this prediction, right? So in this particular case, 3 as a 2 is what is getting confused here. And in this particular case, it's saying, okay, these parts of the image is what is making it believe as a 3, as a 2, and here as 3, right? And similarly for the bottom one. And there are other techniques like, for example, locally interpretable model agnostic explanations like LIME. Both of these, I think, today Vineet will be talking about in the afternoon. And the last one is also synthesize or augment your data as well, right? So if you don't have enough data, try to get them as much as possible. Make sure data is representative. If you're unable to get it, and if you think your data is at least representative, meaning it can be, you can interpolate between them, right? In that case, you can use GANs or other techniques, etc., in order to get data. So here's an example of we using GANs to generate data. And this is it. For example, driverless autonomous driving, they use quite a bit of simulators for creating data. One very important slide is this. So any key slide will have a star. Okay. So now what this is the idea here is that you have to do what is called discipline machine learning. The idea of discipline machine learning is as follows. This is again by Andrew Ng. And the idea is you divide. So usually you have your training set and your test set, right? So the training set is what you train your algorithm initially on, and the test set is what on what you actually you are going to test against, right? And so these two are your data that you use on a regular basis, okay? But you also need to keep 2 other data sets. You need to divide your data into 2 more pieces, okay? And I'll tell you why in a moment. And these 2 pieces are used much less frequently, okay? This verify probably use once in few weeks, and this you might use once in blue moon, right? And the whole idea of having these many of them is that when each time when you are training the algorithm with each of these models, for example, your test data, right? You might be part of the feedback loop that is overfitting the data to the particular model, right? So in order to avoid those biases, you need to keep the data outside. So for example, when we are consulting, we keep the goal data with the customer. We never see the data. We divide it and give it to a customer, and the customer only tests it and tells us whether our model is doing what we're expecting to do. Right? Now the kind of problems usually you will have, how do you go about in disciplined fashion about, should you change your architecture? Should you train for longer, etc.? This flow chart probably will help you. So the common problems we have is what's called bias and variance. That's the first common problem. And bias is where your model is too simple to learn the complex data, right? And the other is high variance, where your model is it's using a very, very complicated model to learn the same data, right? So where you are seeing it's overfitting with a very high degree polynomial. And how can you know when this happens? You can know this by if you plot the training set size versus your error, right? So this is the green one is your the test error, and your training error. If your training error is also very high, that means you are having high bias, right? If your training error is low, and your test error is very high, that means that you are probably overfitting. That is a high variance case. So now what do you do? In the first case, you need to get bigger model, you need to get need to train longer, or you need to get a new model architecture, right? Because your model is not even learning what you need to learn. In the second case, what do? You need to add regularization, right? Or you can get more representative data as well, or new model architectures. And more data rather. And the last 2 are in the case of when you have verify and gold, right? In those cases also, what do you do? And so here I'm just showing the explanation, where there's a gap between human and training set. There's a 10% gap between them. That means your model is not learning, right? Or here, for example, between human and test set, your training set is only 1% error, but the test is actually about 10%, right? That's probably a problem. That's a variance problem. All right. So and so on and so forth. Okay. So to have a discipline mechanism by which you go and you train models. The next anti-pattern is what I'll call about metrics. So one is using incorrect metrics. So the idea of using incorrect metrics would be something like, so for example, I want to detect fruits, okay? And what I'm interested in is number of fruits I'm seeing in a picture. Now, if I look at the overall, if my metric is something to cover, let's say, for example, to measure the area of each fruit, right? And I take the total sum of that, that will probably throw me off. That's an incorrect metric to measure, right? What will be the right metric here? The cardinality, or the number of different fruits you detected, right? So you'd be careful about metrics. More about metrics today Harsh will be talking about in the afternoon. So this is a pointer from here. Next one is what we call what is the bad loss functions. These do not allow these do not allow us to train the model effectively. Okay, so this particular problem is the problem of photo aesthetics scoring. What is the problem? So the problem is this: that given a bunch of pictures, I want to say, is this a great picture or is it a bad picture, right? Or is it a decent picture maybe? So for example, I might say, a 4 is a wow, say it's a great picture, right? And a 1 may be a bad picture, for example, right? So now what do I do? So the training would be, as just we discussed as earlier, I'll give a bunch of images, each of them with their corresponding label saying, this is a 1, this is a 4, and so on. I'll train the algorithm. Now given a new image, I need to make a prediction, right? That's what I'll train. Now, when I do that, right, one of the important parameters is the loss function, which I mentioned, which is used to optimize your model, right? So what does it do? So now let's look at an examples of 3 loss functions, okay? And we'll see which is better for this particular case. So now here, let's say the actual image is a wow image. Let's say, for example, this one, and I predicted it's a bad, right? Now one of the laws I could give is I can say, oh, you know what? Whether I get it bad or nice or good, whatever my prediction is, because I wanted a wow, I'll penalize equally, right? I just give a 1. Now another one could be where I say, you know what? No. If I want wow and I got a bad, which is really far off, I will penalize more, right? Or I could even have one which is in the squared of the b loss, which is even it's even got more power, right? So meaning more bad you are, it will even force you further. So choice of right loss function will decide how fast your model learns or how well it will learn. So it's very important to choose the right loss functions, right? So in this particular case, this might be a good loss function. Now I'll take another case where it might not be, right? The similar example, let's say class 4 is, is it an image of a cat or not, right? And the class 1 might be, is it an image of a dog? 2 is image of a pig, and 3 is image of a man, right? In this case, it might not make sense to say that, between 4 minus 1, they are 2 different classes very far off. I don't need to say that, I want to penalize them too much. Whether you predict, cat as a dog or a pig or a man, it's all the same. You got it wrong, right? So you want to probably use a different loss function. That's the intuition here. Now here's some other properties here, like, for example, it has to be differentiable and all that, but I won't go into them now. The next one is bad distribution of data. So for example, this is a typical example we have seen in many cases where the test data will be non-uniform, and you will have one particular class being very high. So for example, imagine your test data has got 70% class 2, okay, and you run the algorithm, and the moment you run the algorithm, you will get 70% accuracy. Why? Because the model is just predicting class 2. It is not doing anything at all. It is just saying I'm predicting class 2 and I'm already 70%, right? So if it was equal, how much would you get? Only 25%, right? So be very careful about data distribution. Look at the data distribution. The other one is, this is a common one I face a lot of clients when I talk to them. They will say, oh, Facebook has implemented face recognition with 98% accuracy, and I also want it, right? But a lot of nuances of what the problem itself is lost. So for example, here, so let me give you three nuances of the problem. So one is what is called face detection and localization, which is there a face, and where are the faces in the image, right, respectively. The next problem is, given a picture of Madhuri Dixit and I'm saying I'm Madhuri Dixit, being this picture, then I want to say, is this me or not, right? Is this Madhuri Dixit? Which is actually, given this table of data, all you're doing is, given this picture, you want to say, is this picture close to any of these in the first row, right? Now the next one is this is the authentication or verification problem, and the last one is actually recognition, right? Where you given an image, I want to, amongst all the images of all the people in the database, I need to say, is this any of these people, right? This is a much harder problem, right? So there are a lot of nuances about the problem itself, right? And that's why I said, when you are coming up with a business problem, you have to make sure that your business problem is very tight with respect to the computation problem you're solving. And to solve a harder problem, it will take much more time, right? So make it as tight as you can. And and um, and so yeah. So and that's the other problem. And next one is that they will the original images would be trained under good lighting condition, and the algorithm will should work at, let's say, night conditions, or this, for example, here this image which is very blurred here, right? So the algorithm cannot predict as great if you're going to give very bad image quality. Similarly, if, for example, in face recognition, one of the common problems is 3D rotation. If you have a lot of 3D rotation, the algorithm really cannot work well, right? So the kind of constraints your system has got also has an effect on how accurate the system would be, right? So you need to limit your conditions you need to work under. And so a few other things would be like things like implementation problems, like incorrect math or implementation of the math, and other things like information leaks, etc. I'll move on to anti-pattern 3. So anti-pattern 3 is what I'll call, this is a good technique, but sometimes it has problems, which is divide and conquer. This is a very commonly used algorithmic technique, right? So what is the technique here? You take a particular problem, divide into pieces, right? So for example, face recognition, I'll divide that into, I'll pre-process the face, I'll do face detection, I'll segment the eyes, mouth, and nose, and finally I'll do face recognition, right? Now, why is this good? It is good because it gives better interpretability, right? And it's easier to debug. Something goes wrong, you can easily go back and say, oh, what caused it to be wrong, right? And it's easier to improve, and also it's easier to develop also, because I could have each person develop each of these modules, for example, right? So it's really great. But what are the problems with divide and conquer? So one of the problems is that so the error gets accumulated. What do I mean by that? So let's say I want the overall accuracy of, let's say, 80%. In that case, each of these stages should have at least 95% accuracy, right? Because the total error is the multiplication of these accuracies, right? And so because of that, you have to ensure, because it's a multiplication, as you can see here, right? So therefore, you have to worry about that. The next one is that many a time they are not independent. What do I mean by that? When you detect a face and that is given to the algorithm, the next time you improve the face detection, that actually could have an effect on each of the next components. Right? You might assume they're independent, but they might not be independent, right? That is the next problem. The third problem is this, that what I'll call again related to independence, which is improvement cascades. So for example, I got 10,000 images. I train the algorithm. I do what's called ablative analysis, which is to know which part of the algorithm has the most number of errors, right? So here, for example, I'll say 600 images failed on this face detection, right? Whereas all others are much smaller. Now what will be the manager's first intuition? Oh, I should go and solve this problem, right? Because this is where I have the most errors. But actually what will happen is that the moment you go and you go and improve this particular piece, here his 600 images failed because they were 600 very hard 600 images, right? The moment you improve the algorithm here, you also have to improve the algorithm here as well, because these were really hard images to solve, right? So the improvements also have cascades. So general, these problems not only happen in machine learning techniques, but even in any of the deep learning techniques as well. Wherever you have divide and conquer, where you have two stages, for example, two-stage detectors or CRF on top of a DL or a CNN RNN combination, any of those places, these kind of problems occur. Next anti-pattern is what I call general enough versus over general. And this particular problem happens because one of the reasons why it happens is that the sales people, right? They would one of the important metric for them would be the conversion rate, right? You go to someone, you demo the product, you want to have a high conversion rate, but usually sales conversion will be like 5%. Now, which means that the more general the system is, that it can more condition can work under, the best it is, right? But they also want it to be fast and accurate also, right? Now you have a problem. You need the most general solution, and it should also be fast and accurate, right? This actually is a problem, right? Why? Because the moment you want it to be general and fast and accurate, the development time needed is very high, right? And that is a major problem here. Now, so in general, one of the things people should really know about is, what are the kind of variations you worry about, right? So, for example, in case of computer vision, it would be things like scale, rotation. So, scale is like do you care about detecting images of different sizes? Meaning, the object could be either 10 pixels or it could be 100 pixels. Now, that difference makes a computational difference here. Or other things could be, it would be rotated. Would it always be a fair friend looking face, for example, or would there be 3D rotation, for example? So the amount of this condition you need to handle will define how fast you can develop and how good of algorithm can you get very quickly. Okay. The other thing I'll say is low light versus high light and strong light conditions. For example, here, right? There's a strong light here. or other things like occlusion. So all these things, the more you can constrain them, better it is. Now a war story from this is as follows. So we developed this particular application where you wanted to read bank forms, right? Like the one here you're seeing. Now, in order to do that, what you have to do is, first of all, you have to align the image. What do I mean by that? The image could be something like this, where it's not at all aligned, and I might have a template of how I actually want it to be aligned, and so I want to align that. So so I will do this process of alignment, where I detect key points and then I do alignment. Okay. So in order to do that, now we assumed that our algorithm has to work for 360 degrees. Okay, so it can be the original image here can be at any angle, right? In which case, now we spent about 4 to 5 months. We came up with particular kind of markers that actually worked well with this particular algorithm and all that, and we got about 98.8% accuracy. Right now, what actually happened in the field? In the field, the scanner we are going to use is something like this. Okay. Now, what will happen now? What changes? What is the change in condition? I'll only have either 0 plus or minus 10 degrees and 180 plus or minus 10 degrees. Now, in this case, I could actually use the old algorithm and still get 99.9% accuracy. Right? Which means that all that 4 months of effort was just thrown away, right? So had we done that homework of thinking then and there, the business, what the use case would be, the product use case, that would have actually solved the problem, wasted an unnecessary effort. And in general, the thing is that generality is expensive. Choose wisely. And coming back to sales, how do you solve that problem, right? So you can tweak your demos for that particular application. Right? You don't need to particularly necessarily solve the problem in its all glorious generality, in glorious generality, right? And the moment once you have a sales conversion or you have a customer, at that point you can go and generalize where need be. To wrap up, few more things. What I'll say is that managers need to understand the nuances of the problem. Talk with your engineers, understand exactly what the type problem they are solving. Right? There's no magic sparkle here. Another very important thing I'll say is site testing. This is actually make sure that your machine learning team is actually going on the site to understand how the data is being generated. Right? So for example, in this particular case, we are creating this model to understand how students are learning, and the students would enter particular data. Right? And in this particular case, the problem was that we were using words like intermediate, exceptional, and these were 6th or 7th graders, and they did not know the meaning of these words. Now, because they did not know the meaning of this word, that actually affected how they actually would enter the data. Right? So actually being in the field is very, very important for anyone doing machine learning or DL or whatever it is. Right? And another important thing I'll say is the importance of good UI UX. If your UI UX is bad, your reason you're getting bad data or different data could be just because of that. Right? And last, human in the loop is very, very important, which is, many a time the initial algorithm might not be as great, and so you need to have humans in the loop in order to give you initial improvements. So that's another very important. And the last one I'll say, which I myself, the self-confident more than anything else, is don't over-theorize. Right? It's very easy to go and build a very, very sophisticated model, and then actually the business use case not needing it, any of that, right? Or it never being solvable. Right? So it's very important not to do that. So to wrap up, takeaways for managers, there's no magic sparkle. Do systematic discipline development. Don't trivialize. Importance of clean data and representative data. Make sure the data is representative. Right? If I cannot interpolate, if I don't have all the corner pieces of the data, I can't interpolate at all then. Right? And all these techniques we have are all mostly interpolation techniques. Trust your engineers' instincts, but make sure you're solving the right problem. Prototype is not production. Understand that difference as well. And general enough is what we need, not over general. Testing and the importance of UI UX is very important. Man in the loop is very important. For example, one of the customers we have, the initial problem they solve, so this is about photos, creating good albums. And for them, they initially solved it by having 1,000 odd people in India and Bhutan solving it, right? And it's now that we are using machine learning. The previous company I worked for in Bay Area, we were trying to do this directly and we did not succeed, right? So there's a lot of value sometimes in you having humans in the loop. And don't over theorize, and be careful about people who are math inclined who could over theorize. And for that, and DL engineers, crap in, crap out. Check your data. Go step by step. Understand what is happening. Systematic debugging is very important. Build the tools that are necessary to look at your data, and know the tools. And simulate or augment. Discipline machine learning. Have a look at that. The good, bad, ugly of laws and metrics. Be very careful of that. Go to today's talks about them, and also the talk about Harsh and Vineet. Divide and conquer and its problems, and keep up to date with the tools. I cannot stress about this also. There are quite a number of times you would implement something only to learn that there is a tool that actually does it much more efficiently than what we are doing. Right? With that, I am up.
You were talking about testing, verify, as well as goal data, right? So what are the strategies that we should come up with to build an effective test data or like verify and goal data?
Effective goal data.
Yeah.
Make sure that your data is representative. That's the most and important thing. What I mean by that is all the conditions you want to handle, you should make sure the data is actually having that, right? So if it's face recognition and you care about low light conditions, you should make sure you have images from low light conditions, right? If it's data from other ones, it probably won't help you, right? So this is what we call the distribution of data, being similar to the real world as possible.
Okay. In case if I want to build a test data, right? Like, should I start off with like having a subset of the training data, or like should I come up with
Okay,
the new
I'll
test
take
data?
it with offline with you. There's one more question. I'll probably take that also.
Hello. As you mentioned, the tools are very important, right? And when there's a large set of data and it is images, which are the tools which help very effectively for curation or labeling of the image data, because there is any commercial or generalized tool which
So
really
okay, there are companies who are there now who help create augment data. And there are a few tools also. I can probably take it offline and discuss. Is that fine?
Thank you, Sumodh.
Thank you.